So, in our last lecture, we have discussed about only stability. Now, we will gradually move towards the condition of asymptotic stability. So, now, in order to understand asymptotic stability, let us quickly revisit the statement at least. Then, proof I will discuss here today. Now, the statement what it states, this was B an equilibrium point and D as a domain containing origin of the let V a function from D to R be a continuously differentiable function and satisfying this V0 is equal to 0 and Vx greater than 0 for all x belongs to D not is equal to 0, or you can say Vx greater than 0 for all x belongs to D for more non x not is equal to 0. Now if v dot x less than is equal to 0 for x greater than x belongs to D, for all x belongs to D, then x is equal to 0 is stable. We have already means proven till this part. Now moreover, if v dot x is strictly less than 0 for all x in D that is not is equal to 0, then x is equal to 0 is asymptotically stable. So we need to prove that if we just remove this possibility of v dot x becoming equal to 0 for some other point where it is not the origin of the equilibrium, then we can make sure that it will become stable, like asymptotically stable. However, one thing we need to keep ourselves in our mind that we may encounter a system where we can have a Vx that sometimes become 0, but Vx, this statement that v dot x strictly less than 0 for all x, it is like here we have not mentioned the time yet, but this v dot x always is equal to 0 means we can also encounter certain case where v dot x can sometimes become 0, but they cannot be identically equal to 0, and in that case also we will see that the system will become an asymptotically stable system. If you are not able to figure out what I am trying to say by all this, let me show you something like I hope you people are quite by this time you are quite means confident and comfortable with our this benchmark system. Say this is B, then this is K. Now if you apply force, that is a form of impulse force, you just suddenly pull this mass away from this datum node. Say this is our datum node, this is fixed structure, and therefore it causes an elongation of the spring K, and then you release. So the force, if you try to draw its time variation with respect to t, it's like this. This is the type of force you applied. So if I consider this point, it's like means slightly change my starting point of observation. Instead of starting it here, if I start my observation here, then it will be like there is no force applied to the system. However, at that time you will already have your xt is equal to some amount, say x uh, x1t will be x1 0 and x2t will be 0 again, because that indicates the most elongated portion of your spring. Now here, what I am trying to say this, then after that if you can apply your intuition and common sense, you will understand that this spring with this type of force, it will execute a to and fro motion. Basically, if you consider its linear system, then you should get a kind of uh, damped oscillation for this system, like it should oscillate like in your uh, face plane you will get a stable focus like this. However, here interesting things to note, that if you define Vx is equal to half kx square plus half m x2 square, where x1 is your displacement and x2 is your velocity, you will get v dot x with the definition x1 dot is equal to uh, x2 and x2 dot is equal to minus k by m x1 minus b by m x x2, right? You will see that v dot x will give you minus b x2 square. So what it indicates, that whenever your x2 will become 0, v dot x will become 0, and accordingly it states it will only ensure stability, but it cannot assert anything on the favor of means your asymptotic stability, or like state space or like lines will converge to 0. It cannot ensure anything. But do remember one thing, that this is a very fundamental things to understand, that uh, actually this will execute what type of motion? It will execute this kind of to and fro motion. So you will get extreme cases where momentarily your this means when the reversal of this oscillation takes place, like suppose due to one instance, this how these things occur, just try to understand that since you at first you elongate the spring by application of external force, at that time this mass was completely, there was no kinetic energy stored in the mass, but spring stored some potential energy because you elongated it. So it means by virtue of its restoring force, when you release the external force, it will try to pull the mass towards its neutral position. But the time when the mass reaches the neutral position, like when your x1 becomes 0, then mass will gain enough potential energy, and that potential energy, by virtue of that, it will move further, like then it will cause a negative x1, and then after certain instance it will stop, because it will compress the spring to certain extent, beyond which compression is not possible with that amount of means energy, or means whatever you say momentum stored in the mass. So then that mass comes to rest, and then again it reversal of this direction occurs. However, then the spring tries to push the mass back to its normal position x1 0, but whenever mass reach here at x1 is equal to 0, by that time again the mass gain that energy, and it means move further in this direction. So this is what we are getting, that terminating means not terminating, rather the two extreme points of every cycle will have in your phase plane it is this point, like if this is x1, this is x2, then these are the points where your means it is the point like extreme. This one is extreme elongation, this one is extreme compression. Extreme elongation, extreme compression, extreme elongation, extreme compression for a single means cycle. And then for all this your x2 is equal to 0, and it gives you an impression that v dot x is equal to 0. But if we investigate further, we will see that it is not the case. Rather, here also we can show that our system is like our system is executing and or means having the property of asymptotic stability, right? Because our normal experience says that gradually the mass will lose, means this system will lose energy due to presence of friction, and gradually it comes to rest. So that coming to rest implies you are at your asymptotic stable position. However, this you will see that all the time it becomes 0 whenever x2 becomes 0. But what I am trying to say that v dot x, you cannot say identically equal to 0 other than origin. Why? Because if you consider a certain point, say here, at this juncture x2 is 0, right? But x2 dot, what about x2 dot at this point? If you put here, you will see that as long as x1 is also not is equal to 0, a finite x2 dot exists, and that x2 dot will always means compel x2 to move from its 0 value to some other value, or to take some other value. Whenever x2 moves from means these zeros are momentary 0 of x2, momentary occurrence of 0 value for x2 car. So this one will also momentarily become 0, then again it will have some negative values, and that is, it's very important that identically equal to 0 is also an important one. Now we'll see that how mathematically we can reach to the same argument or similar argument. It is like we are trying to bridge the gap between mathematics and physics. Means there is actually no gap. Actually, only gap is due to our own limited vision and perception. So we need to means broader, means have a broader perception and enlarge our vision to understand that how these two are perfectly correlate with each other. Now what we can see that now let us assume that our here say this condition v dot x is less than 0 for all x d that is not is equal to 0 holds, then what we can see that we need to show that this xt tends to 0 as t tends to infinity, right? So basically what we are trying to state, if we means paraphrase this statement, we can write that for every a greater than 0, there exists capital T greater than 0 such that Now, by repetition of our previous arguments, what we can write that for every a greater than 0, we can select b greater than 0. So, what we can have here is that this b greater than 0 such that your omega beta belongs to the ball BA, right? Uh, what is omega beta and BA? If you means I cannot repeat so many times. The definition you can see from here. We are just taking B, and B has to be something uh, based on A. So this we can take. Now it is what we need to show is that Vt tends to 0 as, sorry, V is not an explicit function, so we cannot write it. It is an implicit function of time. So Vxt tends to 0 as t tends to infinity. Showing this one will be sufficient to prove. Now, do remember one thing, that Vxt here also, Vxt is a monotonic function. Monotonically decreasing function that is bounded below by 0. Like if you take all possible values of V, then one thing is guaranteed: the infimum of that set will be 0. Like, what is infimum? The greatest lower bound. The greatest lower bound will be 0. Now, with that, mathematically you can write it like so. If this is the case, we can prove this by contradiction. Like, what we need to show is that Vxt tends to c greater than is equal to 0 as t tends to infinity. Like, we are assuming an intermediate value c. Now, what is we need for asymptotic stability? This c cannot be greater than 0. It must be equal to 0. So let us try to prove this by contradiction. So by contradiction, what we can write, like, let us consider, suppose c greater than 0, which is not in the case, but we want to exploit, or we want to reach our conclusion by contradiction. So since Vx is continuous, we can find out some d greater than 0. So if this d greater than 0, what we will have? Bd contains in omega c, right? So the limit implies that the trajectory outside of the ball BD for all t greater than is equal to 0. Now let us consider minus gamma is equal to max of d. Since this is a negative number, so minus of this this gamma is actually a positive number, so this will give you, and this we should get because we know that for a continuous function we will always get a maximum over a compact set. For continuous function, keep it in your mind, for any continuous function over a compact set, you can always find its maximum value over that interval. So what we will get that v dot xt is continuous and therefore it must have a maximum over the compact set Now, if this is the case, then what we can write that Vxt will be that is somewhat less than is equal to how we can write it, because what is the value of gamma? Gamma is like it contains the maximum value in negative sense. So if you consider minus gamma is maximum, then obviously you are actually claiming that this is the maximum negative that the function can offer. So when you will do it, you will get this one. So here it is clear from this inequality that the right side will eventually become negative, because if you increase this t is the your span of observation time. So if you keep on increasing t for a constant gamma, because gamma is defined here, gamma must be means gamma cannot be negative, because we have proved that v dot xt is means sorry gamma cannot be 0, because v dot xt is not allowed to be 0 over this entire region. So gamma will be a positive number. Now you are multiplying this with t, and here it is a constant. So obviously this will become 0 at a certain time. But vxt, although it's lower bounded, but at the same time it has a constant that it cannot means be smaller than c. Somewhere we have defined it, yes. So it will. So this clearly a contradiction. So what we can write that uh, means that it is like our your this one is asymptotic stable, like no such c exists. What happens is that it gradually means v gradually becomes 0 with increasing time. Now, here one thing we must understand, or rather, let us means introduce a few new keywords to you so that you can conveniently use them. Like any continuous differentiable function that satisfy two conditions. What are the two conditions? Let me write clearly. One is v means continuously differentiable means what? Let me just copy it. That will means reduce our burden. So any continuous differentiable function, only b remains there. We cannot copy b, but anyway, b a continuous differentiable function with this. And then this function is known as the Lyapunov function or Lyapunov. Uh, both abbreviation is possible. Sorry, not abbreviation, but rather in both way you can means pronounce it like Lyapunov or Lyapunov. It's your choice. He was a Russian mathematician, and he has list to do how we means pronounce his name. So it then if it satisfy these two, like means positive definiteness and 0 at origin, then it is Lyapunov function or Lyapunov function. And anywhere if we find any closed path with constant energy, that for some c greater than 0, this is called a level surface or a so what it shows basically, if you think it is like we can always have some Vx. Don't get confused with that. Means if you ask me that in relation with our previous discussion, this one, it is not the constant radius ball BR, it is that omega B. How we defined omega beta, if you recall, then omega beta was defined for all x belongs to omega beta, Vx is less than is equal to beta. So omega beta was just a closed curve, not a regular shaped one like a circle or an ellipse. It could be anything, but it is omega beta. And similarly, omega beta was defined based on the energy value, not based on the distance of your, means based on certain norm of state. So what we can have here in your means state space, these closed curves, like they will form in your, if you consider, try to visualize, these all are Lyapunov curve, where they are distance from, now it may so happen that this is your origin, clearly they are, if you move along that path or along those close curve, obviously your norm of x will vary. Clearly here we have not defined our Vx just as a, like a proportion of norm, rather Vx is having something, some other function, it's Vx, but whatever it's Vx, it has nothing to do with this, irrespective of Vx means definition. If it wants to be at all, means register itself as a Lyapunov function, it has to satisfy these properties, like it must be a continuously differentiable, and it must be zero at origin, and it must be non-negative value, non-negative positive value at all other points except origin. Then we will always get this kind of regular or irregular but closed curve in your state plane, where it will be like just now. One thing you can see here, it is very clear that obviously if you take a small value of c, this curve, although irregular in nature, but they will try to shrink towards your origin, right? Now we already accustomed with the notion of positive, negative, and negative definite. Uh, One question came regarding the calculation of second norm of a matrix. I'll show it, but let me discuss a few examples that may help you in understanding that how things work or how to apply Lyapunov. Like what we can do is that one more thing I would like to mention in this context, that it is like there is no such hard and bound that if your system is with a chosen Lyapunov function, if your system gives you that v dot x, after doing some calculations you find that v dot x is not negative definite, however Vx is satisfying the means properties of being a Lyapunov function, but v dot x is not negative definite, v dot x is means sign indefinite. then no need to lose your heart, no need to conclude that the system is unstable. It simply indicates that your system, you need to carry out the test with some another candidate of Vx or Lyapunov function. So basically, in a nutshell, what we can say that this Lyapunov function, this gives kind of sufficient condition. Like if you are fortunate enough then or experienced enough that in your first run you may pick up a Lyapunov function so suitable and so well defined that for a stable system it fails and sorry, for a stable system it gives you p dot x is negative semi-definite or negative definite depending on the nature of stability, whether asymptotically stable or just stable, and then you can reach to a definite conclusion that if we get that p dot x is negative, then there is no chance the system can have means any chance to become unstable with this configuration. But if it fails, then there is no means no way you can conclude that our system is unstable. So that is now the obvious question that will comes in our mind that so how many iterations or how many times should we means continue this trial based on, like it's like trial and error. If you are good enough with your experience, you are lucky also, you picked up a Laplace function and that gives you a definite result. But if you are not so lucky, you will pick up a Laplace function that ends up with resulting in a sign indefinite uh, derivative. So how to deal with that? There are certain tools for handling that kind of case or circumventing this situation. And then also Lyapunov has given something to means overcome these difficulties. So I will discuss this gradually. But before we go to that, let me take one small example. Like x dot is equal to minus gx, where gx is locally Lipschitz on so this is given. Now we can have a sketch of such gx if possible, like yeah, it could be something. If this is our gx, it will be almost like a triangular function like this. We have to draw it in a symmetrical manner. Right. Now see,
this one, it's very clear and means very powerful example in this way that from this we'll be able to conclude a few things. Anyway, so what is the equilibrium point of the system? Clearly, x is equal to 0 is the equilibrium point where your rate of change of means state ceases. Now, what you will be able to see from this, like here we can get a Lyapunov function like so this will give us a positive definite. Why we are so confident about this defining this? Like you can see that we have already mentioned that xgx, that is product, is always greater than 0 in that interval. So if it is always greater than 0 in that interval, in a layman language you can see that it is also kind of uh, means area under the interval. Whenever you will try to means evaluate, you are actually deal with this. So over the domain v, the way we have defined, we can write vx is continuously differentiable. True. Now see that uh, like we have and also Vx will be like, if you take V0 then it will become 0. So obviously V0 is equal to 0, and for all other value of x, Vx is greater than 0 because your this xgx is not equal to 0, rather greater than 0 for all other values. Now, if we take that v dot x, what we'll get here, that v dot x will be something like, as it is not again the explicit function of time, so it will be del phi del x, and then it will be minus gx. So this will give you that is always less than 0 for all x belongs to d minus 0. So this origin is asymptotically stable, right? Now consider the pendulum equation. Now for sake of simplicity, I can just boil it down to some other value, a, say a. Now for this, uh, one obvious choice you can have, like again considering half x1 square plus half x2 square, but soon you will realize how pathetic this choice is, because in the next level it will result you so you will be stuck in a situation like you are having two, means two two
means signed indefinite part. So you will be in trouble to figure out how to deal with them. So in that case, you may do some mathematical manipulation to get rid of that, but that will also be means need certain maturity. So all the time we cannot means just define Vx as simple as half uh, x1 square plus half x2 square or like that. So we can define here Vx is equal to, here it is a vector, so Vx is equal to a 1 minus cos x1 plus half x2 square. This is a quite rational choice. Why? Because if you from that, if you, I'm not means discussing how this becomes continuously differentiable and satisfying all the conditions or all the prerequisite of being Vx or being Lyapunov function, Lyapunov candidate function. It is by its definition satisfying all these requirements. So here you can see that why this choice is so good, that V dot it will result in. So you will get 0 over here. So this is positive definite over the domain. Here domain, we can define the domain by saying this. But V0 is 0. So now, however, we can see that V dot x becomes 0. So we conclude that the origin is stable, and here V dot x, see one more important statement I am going to make. V dot x, this triple dash means triple equality sign implies identically equal, means forever or without means consideration of time for any time frame or time span, it is identically equal to 0. So here as V dot x is identically equal to 0, we can also conclude that the origin is not asymptotically stable, and that is quite a, means we know that if it is a frictionless pendulum that can oscillate or that can execute oscillation in a free means a free oscillation it can execute, then obviously there is something that means it will be able to continue its oscillation without any such problem or any obstruction. So that is how it satisfies your requirement, right? And but one again this problem has raised one interesting means if you are observant, you must have observed that I have tactically selected a into 1 minus cos x1 plus half x2 square. But this is possible because this is just a second order system. Now if you have a surgical robot and you are trying to analyze its stability, where the robot's degree of freedom is 29th or something, so if that state model is vast enough, say having say 50 state variables, for 50 state variables, and they may include this kind of nonlinear terms or trigonometric terms, it will be extremely difficult for you to find out or to pick up such a is Vx that will lead you to a definite result. Quite often you will pick up a Vx that I have just means I wrote a few minutes back, like Vx is equal to half x1 square plus half x2 square, and you end up in a situation you will find yourself completely stuck, where means you will have no other choice than means trying your luck with a different Vx. So that is very important thing. Two things we have learned from here, that
not necessarily all the systems are stable, means asymptotically stable. Some systems are stable, but for that what is needed is that v dot x is identical equal to 0. It's not positive definite, it's not negative definite, it's identical equal to 0, and that gives us condition that system is asymptotically stable. In some cases you may find that p dot x is not identically equal to 0, but what is happening here, p dot x is like, I will discuss some more example instead of means discussing it over this, you will get it. And one important observation you can see that if you include some friction term, then obviously this friction will make this whole thing, means whole picture will be changed if you include some friction term here. And obviously how you will include some friction term, obviously that friction will be proportional to your angular velocity, right? Whether it's an air friction, obviously we'll consider viscous friction, and that means friction always tries to, what is your x2? x2 is basically your pendulum velocity, and any friction tries to oppose the velocity. It's means universal truth. Means whether it means oppose it in a linear fashion or in a non-linear fashion, but it always opposes motion, so thus it always opposes the rate of change of velocity. So if that is the case, then obviously when you will have another minus bx2, you can see that almost kind of similar argument you will get here. Like you will have here 1 minus bx2 square, and whatever discussion I was doing for your mass spring damper system oscillating and means like sometimes x2 is becoming 0, and then the total things become v dot x momentarily become 0, but not identically. So similar argument you can apply here, and you will reach to a conclusion that v dot x, although it may momentarily become 0 during this pendulum oscillation, but in the long run it will become means it is not identically equal to 0, and that is very very important. Try to register this word, that identically equal to 0 and not equal to 0, and then you will be able to figure out that whenever your x2 is 0 in any other point than that of origin, there is something in your x2 dot equation that is dependent on x1, and clearly x1 is having some values that will again cause motion, further motion of x2 dot, right? That will cause a further motion in x2 dot, and means that due to non-zero x2 dot, x2 will again become or will assume some non-zero value, and this motion means this oscillation is continuously means what to say, that it's dying oscillation. It's this having a certain decay rate, and gradually it means this pendulum, if you allow it to oscillate for infinite time, it will means reach its equilibrium position, and there will be no further oscillation. So this one is known as asymptotic stability. In our next lecture, we'll investigate that instead of trying our luck in random, what systematic procedure we can take. That is one approach, that is known as variable gradient method. But then after learning variable gradient method, we will find that that one also not so good to deal with everything or complicated systems. So we'll discuss that. In addition, we'll discuss some some problems solving using variable gradient method. One more thing I would like to draw your attention that as of now we are discussing only time invariant and also kind of force invariant, means force means it is a force free system, but gradually we need to incorporate all these things in our discussion. So we'll see how we can do that.